just have to catch up. Like Michelle said, my name is Erin Keys, and I am the Engineering and Operations Manager for the Sanitary Sewer and Stormwater Utilities for the City of Columbia. So we are one of the action team members. I've been charged with giving a very brief, it'll be very brief overview of what the CAM is, what the Collaborative Adaptive Management Process is, and that's just to catch up people who are new to the group or visiting these webinars. So it'll be a bit of a recap for those of us that have been in this process for a while, but I'll try to keep it real brief. Probably the main item is if you want more information to check out the website, which is at www.helpthehinkson.org. And Michelle, is everybody seeing my slides okay, I guess?
Yeah, I can see them perfectly.
Okay. So like I said, welcome to everybody. We're excited to present some of the recent work that's been done on the Hinkson, some studies, and we wanted to have this three teams meeting a year ago, and we've had to delay it until now. I think we have a good alternative that may be even more convenient for people to learn this information, and I'm looking forward to the opportunity for us to collaborate with all the teams together. So we can all hear the same information and maybe give each other some feedback on what our next steps need to be. So to kick off, what is the Hinkson Creek Collaborative Adaptive Management Process? Our main goal is to address the impairments of Hinkson Creek relating to low macroinvertebrate populations. So kind of just extremely briefly, how did we get here? Hinkson Creek was listed on the 303D list. So this is a regulatory mechanism to address the impairments on Hinkson Creek. So Hinkson Creek was on the 303D list. There was a TMDL, a total maximum daily load issued for Hinkson Creek, but they were not able to determine what the pollutant was that was causing our low macroinvertebrate populations. So the five parties you see there came to an agreement to use the collaborative adaptive management process to try to address the impairments. One, to try to figure out what was causing the impairments, and then to address that to increase our macroinvertebrate populations. So that's why a lot of what we do, one of the presentations we'll have later in this series will be about the macroinvertebrates and looking a little more in depth into what might be impacting them. So the EPA, Missouri Department of Natural Resources, the City of Columbia, Boone County, and University of Missouri have agreed to use this collaborative adaptive management process. And it is well suited for this complex situation. So for those of you that know, an adaptive management process is a scientific methodology where you assess the problem and then come up with a solution for that problem and act on it, and then you monitor your solution, you evaluate, and then you adjust. Well, the collaborative adaptive management process takes it a step further, and you have a stakeholder-based group that looks at this scientific methodology. So you can also incorporate some of the socioeconomics that are involved in making decisions to, in this case, improve the creek. So at the bottom there, I've got what the stakeholders have put on all of their agendas most recently, and it's their mission. And they require that a project to move forward must clearly and specifically relate to removing Hinkson Creek from its impaired status. And again, the impaired status has to do with the low macroinvertebrate population. So the collaborative adaptive management process has 3 teams. We have a stakeholder committee, which is made up of local interested parties, and they carry out the tasks of the agreement. And it consists of private landowners, business interests, environmental interests, education. We have a member from the school board on there, local government, and then the EPA is our mediator for that process. Then there's the science team, and they're charged with identifying, evaluating, and advancing the different scientific studies to support the process. It includes scientists, professionals from USGS, Department of Conservation, University of Missouri, DNR, EPA, and private consultants. And then the action team, which is what I'm a member of, includes the MS4 partners, and MS4 stands for Municipal Separate Storm Sewer System, so M and 4 S's, and that's our permit holder for this urban area, and that includes the City of Columbia, Boone County, and the University of Missouri. Also on the action team is the Boone County Regional Sewer District and the Missouri Department of Transportation. And we act as a liaison group to carry out the identified tasks that the stakeholders approve. So the CAM Riparian Subcommittee was formed by the stakeholders during this process, and that includes stakeholders and action team members, and I think there's some other ad hoc members. And they're exploring ways to increase riparian areas in the Hinkson Creek, which was an action item. And they are also pursuing funding through the USDA for some rural properties in the watershed to do some improvements. So that is kind of another subgroup of the CAM process that's doing some good work. So some of the official CAM projects that most of these have been completed, and again, you can find more information about CAM on the website, thehelpthehinkson.org. One of our first actions was the physical habitat assessment, and that's where we use GIS to evaluate a moment in time of what Hinkson Creek looked like as far as the geography, geology, how wide the creek was, deep, where there was sediment, where there wasn't sediment, just a bunch of different aspects, physical aspects about the creek. And then, so we'll have that to compare to in the future, should we use it. And that you can find that, there's a GIS link on the website. One of the other early actions was the Forum Nature Area Level Spreader, which our speaker Laura Wiseman is going to talk about today. We had the Flow and Sediment Study, which was performed by Dr. Jason Hubbard of MU, and one of the big things that came out of that was the significance of our riparian areas, and so that was kind of the impetus for starting the Riparian Subcommittee. Then we have the sediment mapping project, which Boone County's been working on, and the El Chaparral Riparian Restoration Project, which that came out of our Riparian Subcommittee, where we're trying to improve our riparian areas. And again, the riparian areas are those areas next to the creek that can either be preferably some kind of native vegetation. Then we have the Aquatic Macroinvertebrate Data Mining Project, which Geosyntec is going to talk about in our presentation April 15th. And then Dr. Argerich from MU is doing a synoptic sampling project of Hinkson Creek. So those are some of the action items that this group has already done. There is a number of other projects that occur in Hinkson Creek that aren't specifically CAM projects, but they're projects that the MS4 partners or nonprofits or private businesses are working on that also benefit Hinkson Creek. So it's good to keep those in mind. The various native planting projects, those are beneficial to our creek. There's a lot of best management practices, and typically, like the level spreader we're going to talk about in a little bit, a best management practice is something that will slow the water down, allow it to infiltrate into the ground, and remove some of the pollutants. And because Hinkson Creek, you know, it has the unknown pollutant that is causing some of our impairment, however we can filter out that water to improve it is going to improve the creek in the long run. We have ordinances and design standards that both the city and county and MU have put into place that benefit the creek when we do any kind of development. Sanitary sewer projects, a lot of projects that the sewer district has done to remove those discharges from sanitary sewer treatment facilities from the creek, that improves the creek. And then education is probably one of we always consider that the biggest bang for the buck as far as improving the creek, because so much of the pollution in the creek is people pollution. So however we can best educate people to take care of our environment in different ways, different tips and tricks to reduce the pollutant load on our creeks a lot of that's through education. And I meant to mention one of the things that occurred and that was back on the previous slide. So for the aquatic macroinvertebrate data mining project, as part of the TMDL process, MDNR did a lot of sampling of Hinkson Creek for both water quality and of the macroinvertebrates. And then once we started this CAM process, they agreed to do, well, initially it was 3 years, but it ended up being 5 years, I believe, of intensive sampling of the creek. And so there's a lot of data there in that sampling. And so that was part of our data mining project, was to dive a little bit deeper into that data to maybe help us figure out what some of the impairments are with Hinkson Creek that maybe we can address with some kind of an improvement. So that is a really fast overview of the CAM process. So I'll see if anybody has any questions at this time, and if not, then we'll turn it over to Laura so she can talk about one of these action projects that we've completed.
I don't have any coming in through the chat, but if anybody has any pressing questions and they want to unmute themselves, now is your time. All right.
Okay. Well, on to Laura. So Laura, are you able to introduce yourself, please?
Oh, yes, I can. Thank you. My name is Laura Wiseman. I graduated from Mizzou last May with my master's degree in civil engineering, and I'm going to be presenting today on the level spreader project that I did with Dr. Enos Innes. And if I can pull up the PowerPoint. Where did that go? All right, are you all able to see my PowerPoint?
Yes.
Okay, all right. So today I'm going to be presenting on my project, the monitoring of an urban level spreader as part of the collaborative adaptive management process. And this project falls under the umbrella of the CAM process because it's located within the Hinkson Creek watershed, and that's what's shown here in this map. Hinkson Creek is here in blue, and then the location of our study site at the level spreader is this red star here. So sort of an outline of the presentation, I'm going to go over some really quick background first on just what is a level spreader, what are the components, what is the purpose, then the objectives of this study, and then I'll continue on to the first part of the presentation, which is calculation of the water balance for an urban level spreader. So how did I calculate with the methods, and then some results, and then finally conclusions and some recommendations relating to how effective the level spreader system is at attenuating storm flows and controlling stormwater. And then after that, we'll probably break and have questions on the first part of the presentation. And then after that, I'll continue on with site selection. So that is the creation of the GIS map tool for the CAM partners, for choosing sites for new level spreaders, the results of the GIS map tool, the results, some field verification, and then I'll end with recommendations and some general conclusions for the entire study. So before we move on, I wanted to show this aerial view of the study area. You can see here in green, that's a small tributary stream that meets the Hinkson Creek here that serves as the source of stormwater for the level spreader. And then you can also see the diverter box, which holds water back, and the level spreader itself. So level spreaders are a stormwater management practice that is usually used to move stormwater out of enclosed or channelized systems and allow it to spread out over a much larger area. Level spreaders are usually designed with the goals of increasing infiltration and attenuating peak stormwater flows from small areas. So each component of the level spreader will have a role in the function of the whole system. When stormwater first reaches the level spreader, it'll usually go through some type of a diversion structure or inlet. In the case of Forum Nature Area, the water source is the small tributary we saw in the last slide, and it flows downhill until finally it's collected behind this diverter box. The box has an underdrain that we will see again later that allows only a small amount of flow to continue down the main tributary channel, and the excess water backs up into the level spreader basin, which is here and here, and it's stilled and slowed down as the water level rises inside of this area. Once the water reaches a certain height, it overtops the level spreader lip, which is this structure, evenly across the whole length of it. It transitions into sheet flow as it overtops the level spreader and moves into the downstream area. So the reason we want sheet flow is because it's generally less erosive than channelized flow. It can move a little bit slower and it can cover over a larger area of the ground, which gives more chance for infiltration. So the downstream area is the last component, and it's just as important as any of the other components because it really has to have certain characteristics that make it ideal for infiltration, for maintaining that sheet flow, and it has to be located in such a way that its stormwater management use won't disrupt its other uses. So that's the location of this study and the level spreader that we investigated. So the two objectives of this study were to characterize the processes that are occurring as the level spreader distributes stormwater into the floodplain. So what's happening? How is it distributing that water? And then using that water balance to evaluate whether the level spreader actually increases infiltration and attenuates the storm flows. The second goal was to use the results along with some other site selection criteria from literature and other studies to develop a tool that will allow different entities in the CAM partnership to find potential sites for new level spreaders. So the total amount of water entering and leaving the level spreader for a given storm can be broken up into these 5 different components of the water balance. Inputs on the left include direct precipitation onto the site and inflow from that tributary that comes from the upper watershed. Some outflows that are here on the right. Water leaves the level spreader as outflow either through that diverter box under drain I discussed earlier or as sheet flow over the level spreader. It also can leave as infiltration into that area behind the level spreader and in the basin area, or as evaporation or transpiration from plants. So in order to use this water balance equation, I had to make a couple of assumptions. First, I set the time interval that I calculated the water balance over so that there was no water left ponded in the level spreader at the end. So that means there's no net storage of water at the beginning or at the end of the time interval. Then I chose the control area, which is the area that the water flows into and out of, to include only the diverter box, basin, and the level spreader. So I didn't include the downstream area in the water balance calculation, except as a destination for water as it leaves as outflow over the level width. And this is because there's not a way to accurately measure how water leaves the downstream area or what volume of water would leave the downstream area. Then the last assumption I made is that there's no input or influence to the level spreader from groundwater. So to start off my analysis of the water balance, I chose 2 different storms to evaluate. Both of them had about 2 inches of total rainfall, but it was sort of distributed in different patterns throughout the time interval. So I chose these storms with 2 inches of rainfall because that was the amount of rainfall it takes to actually activate the level spreader. A lot of the smaller storms, there wouldn't be enough volume of water in that basin area to actually overtop the level spreader, which is what we're studying, so we wanted to make sure that we got enough rainfall. So Storm 1 had a total precipitation depth of 1.9 inches, and as we can see here in this chart, it fell over a single time period of about 8 hours. Storm 2 had a precipitation depth of about 2.1 inches, but we can see that it fell sort of in 2 bursts here, and the smaller one follows the larger one by a few days. So precipitation volume for both storms was calculated by multiplying the depth of rain by the total area of the level spreader and the swale area, which was about 0.7 acres. So inflow for the level spreader, that is inflow through the tributary, comes from this whole 120-acre watershed that's north of the level spreader. And if you look at this picture here, this graphic, the level spreader is shown as a red star again. So this watershed, as you can see here, has sort of mixed development. On the west side, there's some residential, then we have sort of a business park type development over here. And then it also has, 2 ponds that already are fitted with outlets that help to attenuate some of the stormwater flow from this area already. So to model, because this watershed is fairly complex, I wanted to use modeling software to generate an inflow for it. So I used the City of Columbia's HEC-HMS watershed model, and I just modified it to match the current conditions in the watershed and that the level spreader as closely as possible. So as you can see here, these 2 charts are time series results from this HEC-HMS model. Elevation is shown here in gray, inflow is blue, and then outflow is this yellow line. So the reason I showed elevation is because I wanted to compare this modeled inflow to a measurement we got out in the field. And so one of the measurements we had out in the field was depth inside of the level spreader lip. And we had that measured every minute. So I wanted to compare the model to real world data, and that's why I modeled elevation. And I have charts that show this elevation compared to the real elevation out of the site towards the end of the slideshow, if you guys would like to see that later. But for now, the results I wanted to take away from this was inflow. So outflow for the level spreader has 2 main parts, and the first part is the underdrain pipe, which you can sort of see the end of here. The underdrain on the diverter box is what allows base flow to continue down that small tributary stream. And prior to 2019, it was actually an open PVC pipe, but in 2019, an orifice plate, this white thing here, was installed at the end to further restrict flow down the stream. So the outflow for this was calculated as orifice flow for either the perforations in the buried section of pipe or for the 2-inch opening on the orifice plate, depending on when the storm occurred. For storm 1, the pipe was open, so flow through the underdrain was really dependent on those perforations in the underdrain pipe. And then for storm 2, the flow was dependent on this opening in the orifice plate, which makes it a lot smaller of flow. But for both storms, outflow from the diverter box is a small value that occurs over a much longer time period during the storm. And this is the flux that over several days completely empties the level spreader basin. During very extreme events, if water ever were to get high enough, there's also these stop log structures here that water could potentially overtop, but this didn't happen in any of the storms we gathered data for, so I didn't include it in my calculation of outflow. And then the last component is the level lip, which is this concrete structure, and it's just rectangular concrete curves. So to calculate outflow, I use the broad-crested Weir equation. The level lip overtops with only a small depth of water, it's always less than a couple of inches, but because it's relatively long, it still releases a large volume of water in a short time. And we'll see that when we look at the final water balance. To calculate infiltration inside of the level spreader basin and swale, I used the Green and Amped equation for ponded infiltration, and I chose this method because it takes into account the area of ponding as well as the depth of water over the ground surface. I was able to estimate an area to depth relationship for the level spreader, then apply the pressure transducer depth measurements from the site. Other terms that were needed to estimate infiltration related mainly to soil characteristics. Many of these I was able to find from the NRCS Web Soil Survey, which showed that the soil type near this level spreader is a silt loam type. The Web Soil Survey provided a really large range of saturated hydraulic conductivity, or KSAT values. So I did a sensitivity analysis and confirmed that a more conservative and low value of 0.57 inches per hour was appropriate to use in my analysis. And I believe this is also correct because the area around the level spreader has been disturbed and compacted by construction of not only Forum Boulevard, but also the hiking trails. So the end result of all this is that infiltration is the second largest water flux out of the level spreader system. So the last term in the water balance is evapotranspiration, and this is a combination of evaporation from the water surface and transpiration or plant uptake. And evapotranspiration was calculated for the area inside of the level spreader basin. I assumed that evapotranspiration from the site would be equal to the maximum potential evapotranspiration that could occur for a reference short grass surface with no modifying factor. And the reason to have it be equal to the potential evapotranspiration is because for much of the time interval for both storms, the area inside of the level spreader and swale was either fully or partially submerged. The climate station collects all the data we needed to do this calculation over the interval of both storms and the days after. And one interesting result is that because evapotranspiration is dependent mainly on solar radiation, it varies on a daily cycle as well, and it's a lot lower when the weather is cloudy. But on the scale of several days as the level spreader is emptying, you can see that evapotranspiration is not very significant compared to the other fluxes out of the level spreader. But over the scale of a whole growing season, you can see that it would be pretty significant and be a pretty large volume of water. So this is the final water balance for Storm 1. On the x-axis, we have time for 5 days and 12-hour intervals. The y-axis shows volume of water with inputs shown as being positive and outflows shown as negative. So in the data here, blue is inflow from the upper watershed, black is precipitation, gray is outflow, yellow is infiltration, and green is evapotranspiration, but it's really small, and so it's hard to see in this graph. And now on the left here, there are some total volume numbers for each flux in and out of the level spreader, and all of these are in cubic feet. As you can see, outflow from the diverter box and level spreader was still the largest portion of water leaving the site. And at first glance, it doesn't really look like any storm flow is being attenuated here, because you can see this big spike. But actually, this is the level spreader working the way it was supposed to, because all of this large volume of outflow is actually leaving over the level spreader lip. So it's being redirected out of the small tributary and spread out over that flat floodplain area. So this is water being successfully redirected. So then this much smaller and longer part of outflow is actually that diverter box under drain outflow. And this is the only outflow that is actually allowed to continue down the tributary channel. I also want to point out infiltration again as compared to the under drain outflow. Infiltration continues for as long as there is any water retained in the level spreader, and it's dependent on depth, which is why it follows so closely to this outflow. So this is the water balance for storm 2. Sorry. Yeah, this is the water balance for storm 2. This graph is set up the same as storm 1, but in this case, the time interval is 10 days instead of 5 like the previous storm. So we see the same pattern in precipitation and inflow with the 2 rainfalls that we saw in the precipitation slide. As in storm 1, you can see outflow broken out to these 2 components. So the level spreader is sort of this large spike here, and then the diverter box under drain is this much smaller and slimmer piece. So one interesting result that we see for this storm, but not the last one, is that there's no second large outflow of water for the second storm. So this could be just sort of an error in how the inflow was modeled, but it can also be attributed to water depth inside of the level spreader during and after the second peak. The pressure transducers on site show that the water level did not rise enough to overtop the level spreader during the second rainfall, so there really wouldn't be another large peak in outflow like there was for the first one. The under drain outfall is also restricted so much for this storm that it cannot increase very much either. So more of the water has to leave through infiltration and evapotranspiration. Infiltration is also a larger portion of the water leaving the level spreader for this storm. So some conclusions of the water balance. The results show that the level spreader increases infiltration into the soil inside the level spreader basin as it was designed to do. And this is mainly due to the ponding of water in this area. So when water is retained behind the level spreader and the diverter box, it's in contact with a fairly large area of soil for multiple days, and this gives the water a lot more time to infiltrate. Also, while the water is ponded, that depth acts as a hydraulic head which pushes more water down into the soil. The level spreader also allows for a larger volume of water to be in contact with the soil at once. If there wasn't a basin to retain and hold water in, the maximum volume of water that would reach the soil in this area would be from direct precipitation, and infiltration would be a fraction of that amount. So in these 2 charts, we can see a graph of cumulative precipitation for both storms, and that's shown as the black line. Because the basin and swale area of the level spreader also hold inflow from the upper watershed, the fraction of water infiltrated now translates to a much larger volume, and this is shown as the blue line on these charts, which corresponds to cumulative infiltration throughout the whole time interval of the storm. So there's also more opportunity for infiltration into the floodplain area downstream of the level spreader when it's overtopped. This wasn't measured during this study since we focused on the area inside the level spreader, but it could potentially be significant as well. The level spreader also is successful at attenuating and decreasing peak flows in the small tributary. This is mainly a function of how the system works to control flow during storm events and retains water over a longer time period. Peak flows during very large storms are now sent to the level spreader lip to overtop onto the floodplain instead of being allowed to continue down the tributary and out into Hinkson Creek. For smaller storms, the water is mainly retained in the basin and swale and either infiltrated or released in a controlled and slowed manner by the underdrain. So in these charts, you can see for both Storm 1 and Storm 2, flow rate in the tributary is not only decreased, but spread out over a much longer time interval. Sorry. So, okay, yeah. One important note that I wanted to make for this is that this analysis compares flow rate in the tributary at the location of the level spreader, but not downstream or where the tributary meets Hinkson Creek. And one important thing that may happen is that flow is likely to enter the tributary as you move downstream from the land adjacent to it, including some of that peak flow that overtops the level spreader. But this extra water will likely be attenuated not only from going through the level spreader, but also from moving over the land surface. So that is the end of the first part of the presentation on the water balance. Does anyone have any questions on the first part of the presentation?
Hi, this is John Holmes, one of the science team members. I was curious, it all made sense. It was a great presentation, but how far below the level spreader do you see the flow start to reconcentrate into channels flow as opposed to overland flow?
That's a good question. For this study, we didn't focus too much on the floodplain outside of the level spreader. We were more looking at this from a water quantity point of view with regard to how much leaves the level spreader, either as overflow over the level lip or out through the diverter box. Some guidelines from literature say that usually you want to keep the distance from the level lip to your receiving body of water, so that would be a stream like Hinkson Creek, fairly short. So one of the studies indicated that under 100 feet would be sort of the ideal distance, but we didn't measure that for this study area.
Thank you.
Can you hear me? Hello?
Yes,
Hi.
you may want to
So,
speak
yeah,
up a
nice
little bit.
presentation. I've got a nasty echo here, but I'll try to speak through it. So I had a follow-up on the question that John asked. So the infiltration that you measured was in the level spreader itself, and the
Yes.
assumption is it went over the level spreader, actually also infiltrated. Is that correct?
Again, we didn't measure infiltration outside of the level spreader, but the assumption is that at least some of that overland flow would infiltrate, but not sure how much. That would be really dependent on soil type.
Okay, thanks. And then the other question, these storms, what sort of return intervals did they have?
I didn't actually measure return interval for them. I just took both of them having about 2-inch rainfall because that's what it took to actually activate the level spreader lip.
Okay, so where did they are, like on a continuum of small to big storms?
Fairly large storms.
Okay.
Especially for a single rainfall like that.
Great, thank you.
So does anyone else have any questions about the water balance?
Uh, I could just say to sort of help answer Rob's question, the rainfall yesterday was 2 inches, so it was like some of them might have been like that storm.
Okay. Okay.
Although I guess yours were a little more spread out than that. Is that right?
Yes and no. For the first storm, it happened over about 8 hours, and then for the second storm, that first peak of rainfall happened over a few hours as well.
Okay. Thank
Yep. Yep. Well, if there's no other questions on the water balance, I'll move on to the second part of my presentation, which is site selection for new level spreaders. And this is focusing on Boone County and also the Hinkson Creek watershed as sort of the area in which this would be valid. So when I looked at site selection criteria for new level spreaders, I focused on two of the main components. And the first is what area a level spreader would be located in. So what type of an area would you want downstream of a new level spreader? Other studies that have been done on level spreaders, like I mentioned earlier with the 100 feet to the receiving body of water, other studies also focus on characteristics that this area should have that will allow the level spreader to work. So some of the main criteria that I found were that the slope of the land should be less than 8%. Ideally, the lower the slope, the better. And the tree cover should be low to medium. And both of these characteristics are important to prevent rechannelization of the water after it overtops the level spreader and as it's flowing away from it. So at Forum Nature Area, both of these criteria are met. While there's an effort to reestablish trees in the floodplain, there's enough distance between them and they're small enough at this stage to where it's fine. The ground is also flat or very nearly flat, and this keeps water slowed down as it moves away from the level lip. So one way that Forum Nature Area is this level spreader is a special case is that it accepts water from a relatively large watershed. So usually level spreaders are used on much smaller areas like single parking lots, watersheds under 5 acres, or small areas like that. And usually the level spreader itself is smaller in size and much shorter. This level spreader works because it's used in combination with other stormwater management practices. So in the upper watershed, those two ponds already work to attenuate some stormwater at their outlets, and the large basin behind the level spreader also functions to retain a large volume of water. The second component in site selection is that there has to be a need for flow attenuation, so you have to have a source of concentrated stormwater. So this could come from the outlet of a retention pond or a small storm drain system or just a paved area that runoff is concentrated in a gutter before it flows off site. I wanted to develop a tool that could be used by the CAM partners to find locations for new level spreaders throughout the county and the Hinkson Creek watershed. And so I decided that a GIS-based suitability analysis would be an appropriate method to combine the multiple data sets corresponding to characteristics of ideal level spreader sites. To start developing the GIS tool, I found 4 data sets that either establish a source for concentrated stormwater flow or an area that could be used to attenuate the flows. The data I used here was statewide, but I trimmed it down to a more manageable size that my computer could process that included all of Boone County. So some areas that would have concentrated stormwater in a large enough volume to be a problem are main roads such as highways, areas with higher percentage of impervious or paved cover, or locations near known stormwater outfalls. Areas that might be suitable for the site of a level spreader have a lower percentage of impervious surface and a low to medium amount of tree cover. So the goal of combining this data would be to find locations where these two types of areas intersect or are close together. So a successful use of the map tool would show places similar to the level spreader site at Forum Nature Area, where there are impervious surfaces nearby but not dense development, and some tree cover potentially, but not so much that the area is too densely forested. So the first step in my suitability analysis was that I took each data set and divided them up into 10 classes and assigned each class something called a utility value. So The classes are based on either percentage land cover for the percent trees and a percent impervious data, or distance to a feature for the outfalls and the main roads. Once all the data was broken up into the individual classes, each class was assigned a utility value from 1 to 10. And what that means is that a 10 corresponds to high suitability for a level spreader site, and 1 corresponds to a low suitability. So for distance to the main roads and outfalls, the highest utility values were given to areas closest to these features, with the numbers tapering off as the distance increases. For percent trees, the highest utility values were given to areas with under 30% tree cover, and the lowest were given to areas with over 70% tree cover. And finally, for percent impervious surface, the highest utility values were for areas between 20 and 50% impervious. In future iterations of the map tool, these factors should probably be changed, and they can be changed to better reflect ideal level spreader sites. So, for example, the highest utility values in percent impervious could be given to areas with lower percentages. So once utility values were assigned, they were added for each map unit using this equation here. Each utility value was multiplied by a corresponding factor, and all of the factors are a fraction of 1. They're based on how important each characteristic is to the overall site suitability. So percent impervious is slightly more important than percent trees because it affects both source and attenuation of stormwater, but both are more important than proximity to roads and outfalls. The preliminary suitability analysis results are shown on the right, where light areas are highly suitable and darker areas are shown as less suitable. The locations that show up brightest on the map tend to be residential areas with medium density, like these ones on the west side of Columbia, and some commercial developments like these ones. So these areas will usually have light to medium tree cover in the unpaved areas, and enough impervious cover from like driveways and buildings and small streets to generate excess stormwater that would be in need of attenuation. Locations in close proximity to the main roads and highways are also shown to be more suitable than average. In this case, the road serves as the source of concentrated stormwater, and the area directly adjacent to the road is usually kept a little bit clearer of trees. Proximity to main highways and NPDES permitted outfalls were also used to generate this map, but because they rank with lower importance, they show up a lot fainter than the percentage trees and impervious cover data. After the suitability analysis was ran, I selected 2 locations to field verify the results. So the first location was in a residential neighborhood, and I chose it because it showed up on the map as having very high suitability, which you can see here. It shows up very brightly. This neighborhood was located in West Columbia, over near Scott Boulevard and Chapel Hill Road, and within the Hinkson Creek watershed. This area has a good mix of impervious surface and open areas, but as you can see in this photo, most of the open areas are in private yards. And in addition, the slope was pretty steep in areas where it wasn't paved. So this shows that more data is needed for the map tool, especially a layer that shows land slope. So the second location I chose because it's similar to the forum site. It's Hinkson Field, which is just east of Providence Road and south of the Hearn Center and some of the other Mizzou facilities. Like Forum Nature Area, the site's a floodplain, so it's very open and flat. On the map, you can see that it doesn't show up all that brightly, not as brightly as the first location, and this is because of the lack of impervious surface close to this area. As you can see here, there's like a parking lot, but there's not a lot of other impervious surface. So if this site were to be used for a level spreader sometime in the future, stormwater would likely either have to be piped or directed in from off-site. And that's one disadvantage. However, as a downstream area for a large level spreader, Hinkson Field's a better candidate than the residential area. In future iterations of the GIS tool, more layers should definitely be added, especially for land slope and soil type. Soil type is important because only some types are conducive to infiltration, and that's one of the goals of installing a level spreader. Slope is also a very important criteria for the downstream area, and you can't always approximate it with other factors like tree cover. It may also be useful to separate the analysis into two parts, with the first being an investigation of your concentrated stormwater sources and the second being downstream area suitability, since these will usually require different characteristics, and usually a single site wouldn't have both of them. So another strategy would be to set the criteria for the suitability analysis in such a way that it picks up potential downstream areas as being highly suitable, but potential stormwater source areas as being very unsuitable. And then you could look at the resulting suitability map for locations where these two areas meet in close proximity. So on this slide, I wanted to include Forum Nature Area as one last example of how the results of the GIS tool look for a location that is known to meet the criteria for a level spreader site. So you can see that similar to Hinkson Field, the downstream area shows up as gray with only a medium suitability, while the area that would form the level spreader basin has higher suitability, and this is due to the trails and Forum Boulevard and the parking lot over here. So some final conclusions and recommendations. In conclusion, the Forum Nature Area level spreader is successful as a stormwater management practice, and it meets its design goals. So it controls outflow in the small tributary, mainly by retaining a large volume of water in the basin and swale and having controlled outflow at that diverter box. The level spreader also increases infiltration into the floodplain by allowing stormwater more time and a larger area to infiltrate. The GIS map tool is also able to locate sites for new level spreaders, but improvements to the analysis, including more data, especially the land slope and the soil type, and more refined factors of importance are needed, and any results will always require field verification. One last general recommendation I had based on experiences collecting data from the site is that the public was really curious about the research we were doing here and about stormwater management in general and the level spreader itself. And I think that this site, as well as others that are located in public parks and areas, might really benefit from educational signage or more frequent tours or some sort of thing like that. Just to tell the public what's occurring on site, how their stormwater is being managed, how the practices work, and why they're placed where they are. So that concludes my presentation. Does anyone have any questions on this second part?
This is John Holmes again. It strikes me that a selection criteria would be, what's the relative elevation of your flat area versus the elevation of your water source? I mean, if the water source is down too low, it's going to be difficult to get it into the flat area is what I'm suggesting. Did you look at that at all?
I did not. I did not have elevation or slope data that I used in this version of the suitability analysis.
Yeah. Well, the elevation for the flat areas would be easy, but I'm not sure where you'd come up with the elevation for the concentrated flow. That'd be pretty challenging.
Yeah,
So
that's probably where field verification would come into it, because I'm not sure exactly how you would do that.
Yeah. All right. Thank you.
Hey, that's a great presentation, Laura. Can you explain a little bit more the utility values for the percent impervious area? Because that one was different than the other two where, you just picked the kind of some middle imperviousness instead of, the most impervious or least impervious. And I'm just curious why you chose those parameters, just to explain it to everybody.
That's a good question, and I meant to explain that but didn't. So percent impervious in this analysis was sort of what I was attempting to do was capture areas where there wasn't too much impervious surface that you wouldn't have room to put a level spreader and its downstream area, but also areas that had some impervious surface so that you would have a source of stormwater. And so I believe here we had about 20 to 50 or 60% impervious being what I've considered to be the most suitable. But again, this probably needs to be decreased in the next iteration to like maybe 10 or 20% impervious, just because even 50% impervious surface is a lot. So did that answer your question, or do you want?
Absolutely, thank you.
Okay.
The stakeholders are pretty quiet out there, but it'd be helpful to get a little input from them about if this is something that we think we might want to continue to explore as far as putting more of these items in to help with Hinkson Creek, and maybe the science team could weigh in as well if they think that there's, you know, value in spending money on this type of project.
Aaron, this is Rob Jacobson. I've got that echo again. One of the things that I've noted since I'm an avid bicyclist is that there's so many places where you can ride on bicycle trails around Columbia where the trail itself could act as a level spreader. It seems like an opportunity to create areas to pond some of the runoff and create infiltration areas like this. I think it's something that definitely should be looked into more. Over.
Hi, this is Diane Early on the stakeholders group. And Laura, you said that generally level spreaders are used for a smaller area like a parking lot or somewhere where they're concentrating stormwater. In your suitability, did you look at the possibility of lots of smaller level spreaders, kind of like maybe what Rob is talking about, where instead of one, you know, a few large ones, we'd have lots of smaller ones?
Yes, so my suitability analysis didn't have specific sizes of level spreaders in it. All it was showing were different areas around Columbia where the area might be suitable for sort of any size of level spreader. What size you use would really be dependent on how much stormwater you have to attenuate for a specific area or how large your watershed is. So, for example, a level spreader that you have coming off of a parking lot would be a lot smaller than like the Forum Nature Area level spreader that has that really big 120-acre watershed. So it's really quite, seems to be pretty scalable as a stormwater management practice.
Hi, this is Janine Pagan, and Aaron had asked if we thought this should be a thing to pursue. I didn't realize, I've only seen that level spreader off a forum. I had no idea that you could, you know, like obviously scale it down. So I would think that would be a thing to kind of look to the future in different areas, you know, a scaled down version, you know, so you wouldn't have to have such a huge area. So that's just my 2 cents on that.
Yeah, and I see that we have a couple messages, but I'm not sure how exactly to view them.
So Richard Perkins asked what was the cost of the project, and Tom Wellman, who designed it, said we spent less than $50,000 on the design and construction. We don't have the specific cost on that. And then we spent a certain amount of money on the study itself with MU, but I'll have to spend a minute to look that up. But I just want to say I also appreciate the feedback from Rob and Diane and Janine. Thank you.
Once those costs have been incurred, there really are no additional costs. We just continue to accrue benefit, right?
You would have some maintenance to the site. So one other thing that we saw on the forum level spreader is that you have to keep the area around the level spreader and inside that basin fairly clear so that you can still hold as much of a volume of water inside of the basin, and so that once water overtops the level lip, it doesn't reconcentrate because there's a lot of large trees or brush that block the flow. So probably maintenance to it would be the only other cost. Just like with any other stormwater management practice like bioretention or similar things.
Excellent presentation. Thank you, Laura.
Thank you.
I had a question. Can you hear me?
Yes.
This is Carl Scala with the City Council. Yes, it's a wonderful presentation. It's tremendous detail. I'm kind of in awe of some of the modeling. Of course, the modeling is based on lots of assumptions, and a couple of the folks brought up a couple of really interesting points about elevation and slope. Slope is one of those things that we struggled with in a different context. But in terms of refining the modeling, that seems to be a very important kind of consideration in terms of how effective the measurement processes are, and with respect to funding and how effective this can be for the entire watershed. Care to comment on those kinds of issues about refining the modeling?
Yes, so especially with this GIS map tool that could be used to find sites for like different future level spreaders, it really needs a land slope layer. So whether that comes from like the MISDIS, like the statewide DEM models that they have, things like that, it definitely needs a land slope layer so that you can figure out whether that's going to be suitable. As far as measurement and modeling with the water balance, I did use HEC-HMS, which that's generally software that you would use to model like sort of a worst case scenario, like a flood scenario. So a different model that I could have used would have been like the SWAP model, which is GIS based, but the data requirements for that are a lot more intense than something like HEC-HMS. So I thought for sort of the level of detail of a water balance that I was doing, the model that I used was sufficient. Is that what you were asking, or?
Yeah, thank you. I thought
Okay.
slope was rather important, and as
Yes.
a layman, I just thought that was an obvious choice.
Yeah.
This is John Holmes again. I'm curious, you mentioned for the next round of this screening tool, what are the plans for the future for the screening tool?
Well, that's sort of up to the CAM partners. If I haven't already, I will put the folders that I had the GIS program in onto the Dropbox site so then the CAM partners can access that, and then that's sort of up to you all where you'd like to go and if you'd like to use it again or refine it.
Okay, thank you. I think that this was an ideal location that you started at, because, you know, the science team has talked several times about how, you know, it's great having riparian areas, but a lot of times there's these deep channels that just carry the water right through the riparian areas into the creek, and that's what makes this such a good site for this project. And it kind of makes me wonder if maybe the next round should consider floodplains as a screening criteria, just because you might have that situation.
I think that might be a good idea, yeah. Floodplains do have a lot of the characteristics that I saw just from different literature, like sort of flatter slopes usually, and sometimes they're a bit more open, so they might be good locations for more level spreaders.
Yeah.
Hello, this is Enos Ennis. Can you hear me?
Yes, hi Dr. Ennis.
I just wanted to thank you, Laura. That was a great presentation. And I know one of the things that we had talked about when we looked at creating this tool is to get the CAM partners thinking about the use of these level spreaders throughout. And again, to reiterate what's been said, smaller, more spread out. But then having that tool, I think, helps folks start to really get in the mindset of, and I like the conversation that's happening here, of where could it go, and what sort of things are we looking for. And with that public education, I think you may have more people in the community wanting to see level spreaders in their areas. And so that's kind of the hope that we had when we put together the this particular tool to then hand over to CAM.
Yep.
One other issue that occurred to me, this is Carl again, and that is in some of the areas where there is a significant amount of impervious surface, and particularly around some of the roads, some of these roads obviously are curbed and guttered, and some of them are not. And are there any considerations in those kinds of areas for influences on some of your data and some of your modeling?
Not in this version, no, just because the scale, this first version of the map tool really looks at things from sort of a very large, big picture scale. It definitely, if you wanted to look at it at a more site-specific basis, just on a, like, one section of road or something, definitely whether there's a storm drain system existing there already or not would definitely have an effect, yes.
Thank you.
Well, that's been some great comments and great conversation. Did anybody else from Action Team or stakeholders or the public or science team want to weigh in on thoughts or ideas of level spreaders and how we should move forward with implementing that, or anything?
Well, one final comment about anything, since you put it up, has to do with a preoccupation that some of us on the city council has with information and how we get that to the public. And you mentioned that, and to encourage this discussion, obviously the level of detail, I'm just a mere neuropsychologist, and the level of detail here in this geo stuff is kind of stunning to me. But nonetheless, getting that kind of message to the folks on any issue other than trash these days is very challenging. And it requires almost one-page summary data. And how would you suggest that I'm not laying this on you, but it's always a challenge for communication. As long as you can generate interest, that's one thing, but to get people to engage in some of the discussion, this is going to have to be simplified to some extent to make them, to encourage them to engage.
Well, one thing that back when I was a student at Mizzou and working with the city, one thing that we discussed was maybe putting some educational signage out at the site. So I know with the forum level spreader, when I was out collecting data, I would sometimes have people stop by and ask me, what this was and what I was doing. And so I think some form of signage out at the site would really help people to know what it is, and maybe why it's there, and why during rainstorms water backs up close to the trail, because I'm not sure some people understood why that was happening. So I think public education is really important, and putting it in simple enough terms that the public would be able to understand quickly is important as well.
Yeah, it's a great idea. Thank you.
And if I could add to that, I know, Laura, probably one of the challenges you had was you're just downstream from the 3M wetland area where there is quite a bit of signage. And I think the city did go through some effort to do little tours through that area, and so being able to duplicate the 3M project elsewhere may be part of the step forward.
As part of a stakeholder committee, so if we happen to see an area that we thought, I wonder if this level spreader idea would work, who would we say, we obviously wouldn't send, coordinates, but more like, an area, street, streetwise, or, neighborhood area, or a trail area, or a park. Who would we send our suggestion to?
That's a good question. You could probably send it to me if it's in the city, or send it to Nikki or Michelle if it's in the county, or I'm not sure who at MU would like that. But if it's on campus, I'm not sure how many spots on campus there might be. I do know that Tom is always looking at opportunities and areas to implement different BMPs such as this. We've always got our eye on some. It's just a matter of trying to prioritize that in with hard infrastructure that needs replacement and that sort of thing. So that's something we're working towards, is trying to integrate some of these green infrastructure practices in with the other infrastructure we have to replace.
Yeah, this is Todd Hatz from the university. For the university, anybody in environmental health and safety, we're all very close. So John White, myself, if there was something identified here and you wanted to let us know about it, we'd be very, very pleased to get that information. I also want to build just slightly on what Carl said about when he mentioned like a one-pager, that the idea of signage is great, but for me, in order to sell this concept or any concept to administration at MU, that's the kind of almost, really not dumbed down, but just really simplified of this is what you tried to do, this is what we found. That's about all I can get in front of somebody, would be a single page of paper. And for anything that's improving the Hinkson, being able to figure out both from your scientific, very heavy scientific way of looking at things, but how can you provide something to get to the audience that are just not going to understand that or not going to look at anything in any depth, would be extremely helpful.
Yeah, I have to say I appreciate that because that's one of the biggest challenges that we have in the political realm these days, is to engaging people with something. And there's a whole range of folks. I mean, I have a academic background too, but it's been a lot of years since I delved deeply into some of this detail. And to the extent that we can have some sort of an executive summary with footnotes, if necessary, if people want to dig into it, that would be very helpful. I love that idea about the signage because on a basic level, that's important. The visual stuff would be great, but I can't emphasize enough and follow up on that last comment that this is essential even for people who are relatively sophisticated in their own areas, not necessarily in hydrology.
I think that's all some great feedback. I think we can definitely take some of that back to the action team and figure out what our next steps just for this one project might be, to be able to keep moving forward. So I don't know if anybody else has anything they want to share or comment on. I don't know if Michelle has any parting comments or statements about maybe the next presentation.
Yeah, the next presentation will be, you'll be able to reach with the same link that was sent out. And if you guys have any troubles, just feel free to email me, and I'll try to help figure that out for you all. And it'll be Cody will be presenting and talking about the macroinvertebrate study, which should be pretty exciting. And I just want to thank Laura again for I was very enthralled with all the work that you've done. It's pretty amazing. So thanks for sharing.
Well, thank you for allowing me to present today.
All right, and yeah, thank you all for attending, and I will send you guys the link as soon as we're able to process it up on our website. So if you want to share with any of your friends, you are more than welcome to, and invite anybody who you'd like to come along. All right, thank you all.
Thank you.
Thank you.
Thanks,
Stay
everybody.
safe.
Thanks again. Bye.